Okay, in this lecture, we're going to go a little further and talk about operators in more detail in terms of mathematics. This will be beyond what you usually cover in a very introductory quantum course, but we want to give a little bit more rigor here. So some of these definitions and operations we'll introduce here will tie in later to actually how they're represented in quantum mechanics and the significance of them. I might just mention them here, but we'll see the significance later. So first of all, recall that the operators are just mathematical entities that act on functions. So we take an operator O, we're going to use that little caret on top to indicate operators. In advanced notation, that's not often there, but we will keep it here. That operates on a function, you get another function back. And so an example we talked about was the derivative operator. Again, by itself, it doesn't have any meaning. But also the placement of the operator is important because it acts to the right. Well, derivative symbol usually acts to the right. For example, f of x times d of x, what does that mean? Function times the derivative, and the derivative is not acting on anything. Seems like nonsense in a sense. So the placements are important and as we go forward. And also, in this quantum mechanics especially, we're talking about linear operators. And within quantum mechanics, it's a theory of operators. There's a lot of analysis in terms of operators, but we always deal with linear ones. And quantum mechanics is a linear theory, it's said. The definition of linearity here is going to be that an operator acting on, say, the sum of two functions is equal to the operator acting on each and then summed. So that's what we mean by linear. And you could check for yourself if it were not linear, like if it was a square, then that would not work out. So one operator we talked about was the identity operator, which just does nothing to the function. It's a trivial one. We also want to consider products of two operators. We saw this in an earlier lecture. That we'll take omega, lambda act on f. Again, the way we think of that is that the order is important. Lambda operates on the function first, and that returns a function, and then omega operates on the resulting function. And so it operates from inside out in that way. Now, the critical thing here is that the order of operators is important. This is a deep, significant property of quantum mechanics. So it could be that operating on lambda on f, then omega, is not the same as omega operating on f, then lambda. And we'll look into an explicit example in a moment. To discuss that, what we do is we introduce a mathematical entity called the commutator. And this is actually introduced in quantum mechanics. And basically, it's given by this square bracket here of two operators. And it's defined just as the product of the operators minus the product in the reverse order. And clearly, if you have two operators the same, omega, omega, it's going to vanish. But it's important to distinguish whether this commutator vanishes or not. If it does vanish, that means that omega lambda is the same as omega lambda, and that has a significant importance in quantum mechanics. But sometimes it does not. I'll show an example in a moment, one that does not. The other property is an inverse operator. An inverse operator is omega to the minus 1, for example. It's when you act on it with the operator, you get the identity operator. And again, the inverse operator always commutes with itself, or with the standard operator, so the order doesn't matter. So omega to the minus 1 times omega is the same as omega times the inverse, and equals the identity. Okay, let's take a look at a specific example from classical physics, and that's the rotation operator. So this might be familiar to you if you've done a little bit of linear algebra. But we want to consider three-dimensional space, vector space. Okay, so we have a vector v. We're going to represent it in this notation with the bracket, or bracket, or bra vector we call it. So this property, this entity here is, we call it a bra vector, or ket vector, excuse me, we call it a ket vector. However, just think of it as a vector for this case, so we're just different notation. And again, what we have, just like in ordinary going back to your basic physics class, we have unit vectors, which we're going to call 1, 2, and 3. Ket vector 1, ket vector 2, ket vector 3, they're unit vectors. And so we can describe a vector by expansion in those unit vectors. So we want to define three rotation operators about each of the axes. So we'll call it the R1 theta 1, R2 theta 2, and R3. And that will take the vector and it'll rotate the vector. We'll think of this two different ways. But again, for example, rotating about R3 and by angle theta on V, we just operate through, and since it's linear, rotations are linear in this sense, we don't really necessarily need to change the components of the vector. We can just rotate the unit vectors as well. This is a different type of transformation. But we can just look at the effect of how the unit vectors are transformed. And again, if you studied at all, you can know this is represented by cosine theta 1 plus sine theta 2, and so on, which can be represented as a matrix, especially if you have finite dimensions here, which is cosine theta sine theta 0 minus sine theta cosine theta 0, 0, 0, 1, acting on the original column vector now. And again, here we define that the unit vectors are 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, so let's just look at some quick examples here of how this works. So let's take a rotation about R3 and then rotate it back. So that means we're going to act on the first one. We would take theta to be negative theta in this first matrix, multiply it by B, and then multiply it by the R3 matrix. That, carrying that out using, again, if you're not familiar with matrix multiplication, you might want to review it quickly. It's very basic and it's handy and it's important. But when you multiply these two matrices together, you get cosine squared plus sine squared, and we see that becomes the identity. And again, just means that if you rotate something through an angle theta and you rotate it back by that angle theta, you get the same orientation of the object. Now what I want to do is take, this is a nice example, and I suggest you do it. So here I have 3 dimensions in space, and I can represent them by unit vectors. I can, like this. And what I want to do is take a book and rotate it about 2 of these directions. So let me start. So start with a book orientated like this, and let me call the green one 1 or the yellow one 2. And so let me consider 2 rotations. I'm going to start with the book in this orientation, and I'm going to do the rotation about 1 first, like that, by pi over 2, 90 degrees. And then I'm going to rotate by that one by 90 degrees, like that. So notice, remember the orientation of this book. So we go back to the beginning, and now I'm going to do it the other way. I'm going to rotate by around R2 first, and then I'm going to rotate around R1. And notice the orientation is different. That means that rotating, the order of rotations is important. And that also says that the commutator R1, R2 through angle pi over 2 is not equal to 0. It doesn't vanish. So the order of the operators are important. So let's look at another example where this commutation relations come into play. And this is one directly related to quantum mechanics, but we'll see later. Well, I can tell you right now because X is our position operator, we're going to call it, and D, notice, is a derivative. That was much like our momentum operator. All I'd have to do is attach a minus IH bar there, and I'd have my momentum operator. But let's just consider it a derivative operator for the moment. And I want to consider these 2 operators acting on a function f. So the question is, do they commute? So notice here, I'll do it in one order here, x df. So that means we're taking the derivative first, which is taking the inside part first, and then multiplying by x. So that's just equal to x partial x. Now we do it in reverse order. We multiply by x first and then take the derivative. Notice now that the first operation just gives us an x, but now when we take the derivative, we have to use the chain rule, so we get f plus x times delta f. Partial f partial x. So they do not commute because we do not get the same function. And we can calculate the commutator here just by plugging in here if we want. Again, the commutator has to be carefully treated here because you always have to act on the function. And what we get is minus f out. So it's not equal to the identity, or actually it's equal to the minus identity, I should say, but it's not equal to 0. So, and again, to find the commutator, you should always have it act on a function, because that's a common mistake in people first learning quantum mechanics. Okay, now let's just talk about some important operators and some notation. So the next thing I just want to, we discussed this before, but again, just repeat this, that given an operator, a linear operator satisfying some special things. There are a special set of functions f that have the property that when the operator acts in the function, you get the function back, just multiply by some scalar function. Not function of the independent parameters x and t here, but just some scalar, we could call it. So the f are called eigenfunctions, and there could be several, and omega is called the eigenvalues. And again, omega is not dependent upon x and t, because then that would be a different function, and it would not satisfy that property. So the way we write this often is that for a particular operator, there are a set of functions f sub I, each that returns the eigenvalue omega sub I, which is the eigenvalue, and there's going to be a set. And depending upon, in a nice case, there's as many distinct eigenfunctions and eigenvalues as there are dimensions of the operator. Okay, so again, this is an important aspect, but it's just notation right now. And these take special forms of eigenvectors and eigenvalues. Okay, now some actions on operators. I want to introduce two. And I'm going to represent these in matrix form. They do have an analog in terms of partial derivatives, or sorry, in other ways. But I'm going to it's easier to represent these in terms of matrices. And with matrices, we're going to have a finite dimensional system, so actually it turns out to be easier to treat, but we will just introduce these for now. There are more formal, full definitions, which we'll save for later. Okay, the first is the transpose. The transpose, if I represent the operator as a matrix with these elements, here's just a 3 by 3 matrix. Again, it could be n by n if we want. There's two ways to think of this. One is that if you represent each one properly a matrix with subscripts where row column, so again, row 1, column 2 there, all you have to do is flip the subscripts. That's one way to think of the transpose. The other way, in a more global sense, is think of the transpose of it as flipping these around the diagonal. So the diagonal does not change because if you flip those indices, it doesn't change. But notice that M31 goes to M13 over here. So we've just kind of did a mirror of the matrix about that diagonal. So that's the one property. The other one is closely related. Is just called the Hermitian conjugate. It's a fancy name, which is defined simply as the transpose complex conjugate, or the complex conjugation transpose. It doesn't matter. The order doesn't matter there. So that's just, again, we flip around the diagonal, and then we take the complex conjugate. And this has an important the Hermitian conjugate is a property you'll see throughout quantum mechanics. But with these two, really a Hermitian conjugate, I wanted to find two classes of operators that are central to the study of quantum mechanics. The first is what's called the Hermitian operator. A Hermitian operator is one where if you take the Hermitian conjugate, remember flipping around the diagonal, taking the complex conjugate, you get the same matrix back, or same operator back, I should say. And so, yeah, and the import, which I don't prove, which is going to state, is that Hermitian operators have real eigenvalues. That is significant in quantum mechanics because whenever we do a measurement of some property out there, we get a real number, like the position is a real number, the momentum is a real number. Those operators are going to be represented by Hermitian operators. So observables, it says, are represented by Hermitian operators because they have real eigenvalues. The other is a unitary operator, which basically says that given the operator u, I'm just calling u just to classify that as that, the inverse is equal to the Hermitian conjugate. So that in that meaning that u dagger is equal to 1, or u dagger u is equal to 1, doesn't matter which way you say that. The unitary operators have an importance in terms of the evolution of a system. If you want to take something from one time to another, you act on it by a unitary operator, the state of the system, and that tells you how it evolves in time. And we can explore the significance of that in a later lecture.